Hey, welcome back. This is Calc 3. We're going to look at doing multiple integrals today. Apparently my little freaking plug just came unplugged. Let me find that. Sorry. Okay, so we had the partial derivative. Now we kind of have the partial integral, I guess you could call it. You can integrate with respect to y and or with respect to x. Okay, so imagine you have a function xy. We'll say something like xy plus 2y, right? If you took the partial derivative with respect to x, it would be y plus, I guess, 0, just y. Okay. Then you can actually integrate with respect to x. So the integral then of y with respect to x, you basically can treat y as a constant. You could even take it out of the integral altogether if you wish, and then it's just the integral of 1 dx, which of course is x. So you'd have y x. But then if you compare and contrast this recovery with the actual function, you'll note that there was this guy that was completely annihilated, right? So instead of just having plus some constant, now you'll have plus some constant that's dependent on some variable, the opposing variable, if you will, the one that potentially got annihilated. Okay. Okay, we'll continue with this idea later in chapter 15 and explore that further. For now, what we want to deal with, though, is finite integrals, where we're actually evaluating and getting some sort of particular answer. So there'll be values in the limits of the integral. Okay. Okay, so let's take a look at those guys. Maybe go to some homework here and look at problem 1. So I have the integral from 0 to x of 8x plus 8y with respect to y. Okay. In this case, the integral of x, you just pretend x is a constant, like 3. If you integrated 3 with respect to y, you would get 3y. Okay. So here, instead of 3y, you have xy on that first one. Then plus the integral of 8y with respect to y would be 8y squared over 2. So you get 4y squared. And then we just evaluate it from 0 to x. We don't have to worry about that weird annihilation of the y variable, or in this case it would be the x variable. All right, so once you get set up like this, then you're just plugging in x into the antiderivative wherever you see a y. So you'd have x times x, so x squared plus 4x squared, and then minus, it'll apparently just be 0. Okay, combine like terms, you get 5x squared. So it's no big deal. It's a little tricky, clearly, a little different, right? It's going to take some practice. So let's try number 3. The integral x cubed to square root x of, and we're doing both of these. Do they have one with respect to x? Oh, here we go. Let's try number 4 then. Okay, so number 4. The integral from negative square root 5 minus y squared to square root 5 minus y squared. And those bounds, those limits there, actually are curves, the right and left hemisphere of a circle. Anyways, we want to integrate x squared plus y squared now with respect to x, right? So integrating x squared, that's just business as usual, x cubed over 3, plus the integral of y squared, that's a constant, so you have to tack on an x, so you get xy squared. Then we evaluate this antiderivative on these limits. So plugging in the top, we get 5 minus y squared to the 1/2 cubed. So that's going to give me 3/2, 5 minus y squared over 3, plus and we're plugging in for x, right? So y squared times the square root of 5 minus y squared, then minus, the first one will be negative 5 minus y squared to the 3/2 all over 3, and then minus, again, a y squared square root 5 minus y squared. I guess combine some like terms there, so there'll be 2 of these 5 minus y squares to the 3/2 all over 3, and then 2 of the y squared square root 5 minus y squared. Okay, all right, let's plop that in just to make sure I'm right. So 2 thirds 5 minus y squared. I hate it when it gives me extra parentheses. 5 minus y squared to the 3/2 plus 2y squared times the square root of 5 minus y squared. And then, yeah, that's it. Okay, great. Right, so from there we want to work with iterated integrals, and the idea is pretty easy. You basically just do the inside integral and then do the outside integral, as you see there in example 2. The outside integral, they note in here in the book, you need the constant, just regular numbers on the outside limits of integration. And yeah, so let's try some of those. We'll try number 5 first, I guess. So I have the double integral from 0 to 6 and then 0 to 5. Okay, maybe I should title my sections like a good teacher, right? So this will be section 2, iterated integrals. I just call them double integrals. Yeah, we have x plus y, and then first we do it with respect to y, and then we do it with respect to x. So if you want to, you can think of it like this, and you do this inside first. Do inside foist. Okay. All right, so on the inside there, integrating with respect to y, you'll have xy plus y squared over 2. And you have to evaluate this thing from 0 to 6. So you're plugging in 0 and 6 and wherever you see y, so you'll have 6x plus 36 over 2, which is 18, minus, plug in 0, you just have 0. Okay, so we just get rid of that. And then you just integrate this with respect to x, and you should have your answer. Okay, so going ahead with the integration now. 6x squared over 2 is 3x squared plus then 18x from 0 to 5. So you get 3 times 25 plus 18 times 5. And then I guess minus 0. So it looks like we get 75, and then 18 times 5, 0, 4, I guess 90. Add those together, 5, 165 for our final answer. Okay, pop it in there and just make sure it's right. Right, so, you know, like I said, it's pretty simple. You just have to kind of get used to it. Let's look at number 8, I guess. The integral from 3 to the 5, then the integral from 1 to the square root x. Then we got 2y e to the negative x dy dx. Okay, and you could have dx dy. It doesn't matter. Just be careful that you're doing it with respect to the appropriate variable. So now in this case, with respect to y, so you kind of just think of e to the negative x as a constant and integrate the 2y part. So you get 2y squared over 2, so that's just going to be y squared e to the negative x, evaluating from 1 to square root x dx. So plug in square root x wherever you see a y. So square root x squared is going to be an x e to the negative x. And then minus, plug in 1s, just e to the negative x dx. Sadly, it looks like we have a by parts right here. So I have to integrate that thing by parts. So let me just kind of do a mini integral over here. U is Lie, so algebraic before exponential. V is negative e to the negative x. Du is just be dx. If you want dx there it is. U times v, so negative x e to the negative x minus the integral of v du. So that'll become plus integral e to the negative x. And then, of course, that will be negative x e to the negative x minus e to the negative x. All right, so then the integral of this part is going to be a plus e to the negative x. So this part and the integral of that part will cancel each other out. And you'll be left with negative x e to the negative x. And then we evaluate on the outside limits, so 3 to the 5. And so you get negative 5x, negative 5 e to the negative 5. Negative 5 e to the negative 5. Jeez, I'm just need to put the x in for some reason. And then minus will become plus 3e to the negative 3. And that looks like it. That's your answer there. Okay, so let's put it in there. Negative 5 e to the negative 5. And then plus 3e to the negative 3. And then try it. Yay. All right, so anyways, there's that. The next kind of thing is we have to kind of visually see what these guys represent. Okay. The visual picture on the first one, you're kind of think of this as going from the curve y equals 0 to the curve y equals 6. So in the xy plane, y equals 0 would be this line, and then y equals 6 would be up here. So you're kind of going, you always think curve to curve and then point to point. So you'd be going x equals 0 to x equals 5. So x equals 0 to x equals 5 would be like that. And what you're integrating is over top of this rectangular area. Okay. The second integral, it's going from y equals 1 to y equals square root x on the inner integral. So if I were to graph that, y equals 1 is, let me maybe put it in a different color. This is like this line. Y equals square root x is this curve. And then going from 3 to 5, right? So from maybe 3 to 5. So again, you think curve to curve, here to here, and then you're going point to point. So the region you'll end up integrating over is this region in here. Okay, so they kind of want you to be able to identify those regions off of the limits of the integral, and then they want you to be able to set up integrals based off of the geometric region that you're working with. Okay, so that's kind of what they're talking about there in figure 14.1. Anyways, from there, yeah, they're going to kind of visit this idea of the area of a region between curves. Okay, so the area of a plane region. And technically, you've kind of already done this. So recall, if you wanted to figure out the area between like g of x and f of x, this region from some point A to some point B, they just happen to be intersection points here. So let's put G on the bottom and F on the top. In order to manage that, what did you do? You would go integral of, and then with this orientation, you have F on top, so it would be F of X and then minus G of X from A to B dx. Okay. So now with what we're doing here is you can embed those F of X and G of X on the inner integral. Okay. So you have the integral from the bottom curve, which is G of X, to the top curve, which is F of X, of 1 dx. Okay. So, I mean, you're getting the area of that space, but technically it's also the volume of this kind of weirdly shaped object. They would call it a cylinder because the bottom and the top are kind of the same, but it has, you know, height 1. So the area and the volume are exactly the same. Right, so think about a cylinder with height 1. What would be the area of that, or what would be the volume of that object? Well, the volume of that object is just the area of the base, which is pi r squared, times the height. So if the height is 1, the volume is basically just the area of the bottom. It's just pi r squared, right? It's the same idea here. What you're doing is kind of finding volume. It's just that the height of the object is 1. Okay. But anyways, long story short, you can achieve this integral using a double integral in the way I've just written, because if you integrate this inner part here, you'll have the integral from A to B, and then the integral of and we should have with respect to y first, right? So this would be dy, and then on the outside dx. So you would have y evaluated from g of x to f of x, and then you go dx. And of course, there, when you plug in g of x and f of x, you know, you have f of x minus g of x dx. Lo and behold, you get back to our Calc 2 integral, right? Okay, so you're finding the area between two curves, or you can technically think of it as the volume of a cylinder with that kind of base and top with height 1. You can think of it either way, but when we do these, we need to have simple regions, and simple regions just means that that we can basically go curve to curve and then line to line. So this vertical region, you see the boundaries on the left and right are vertical lines. That means it's vertically simple. Okay. Horizontally simple is just the other orientation. So you imagine you're running up the flagpole, so to speak, going up the y-axis. The top curve would be the right curve, the bottom curve would be the left curve, and then the bounds on that going from point to point, the C to the D, those are horizontal lines, so that's considered horizontally simple. Okay, so there's those ideas. Anyways, the first kind of problem that you encounter is just finding the area of a rectangular region. Let's maybe see if they have a corresponding problem here. So, okay, so they have the area of a triangular region, which I think is kind of the same idea. So I guess we're going to be stuck with that if we... Now, let's do a rectangular region just to stick it to them. Let me find a nice little example. Find the area of the rectangular region. And there's nothing sacred about the order that you do it in. You could do dx dy or dy dx with these really simple regions like what we have in this case. It's not going to matter. So let's pretend we have this region that we want to figure the area of. We know the area, of course, is just 24, but let's see if we can use a double integral to figure out the area. Okay. So the way I think of it again is I'm going to go, and the way I'm going to do this is dy and then dx. Okay. So for the y part, I think curve to curve. So y equals some curve, and you don't write in y equals on your integrals, but you can if it helps in the beginning. But I'm going to go from the curve y equals, and I think I'll go from y equals 0, this curve, to y equals 3, right? So I'm going to go from that curve to that curve. Y equals 0 to y equals 3. And then x, you're thinking point to point. So you're going from x equals 0 to x equals 8. So you're going from here to here and integrating in that direction. So x equals 0 to x equals 8. And that should give us our answer. Okay, so let's see if it works. I have the integral of 1, which is y, and I'm going from 0 to 3 dx. Evaluating y on those limits, it would just be 3 dx. And then that would be 3x from 0 to 8. And that would be 3 times 8, which is 24 minus 0. So yeah, we get the area of that region. Okay, dandy. Let's look at maybe some of these other ones. So in the software here, first they're just having you kind of they tell you the order they want. So I got this double integral. They want dy dx. So they give you a picture here, and it looks like the curve is just y equals x, this curve here, and they're going from apparently 0 to 6 right here. So again, I think curve the curve. So the curve y equals 0 to the curve to this other upper curve, which apparently is y equals x. Okay. Then on the x-axis, you're going from point to point, so you're going from this point 0 to this point 6. Okay, so x equals 0 to x equals 6. And of course, in the software, you just plug in 6. Don't put x equals. Then y equals x. And then they want you to integrate the thing. So the inner integral, the integral of 1 with respect to y would just be y. And then we're going from 0 to x. Then I'm integrating or evaluating y on those limits. So it'd be x minus 0 dx. And then the integral of x with respect to x is x squared over 2 from 0 to 6. It's going to be 36 over 2, so 18. Okay, great. So there. Okay, so what's the hex number 15 then, right? Don't spend too much time on. Let's not spend too much time on these. This one just looks weird. Okay, so this one's dy dx. So dy dx, our little region here. Looks like we have 9, and then 1, 2, 3. So I have this line. I'm going from 1, 2, 3 to 9. Okay. Okay, so curve the curve, right? Curve y equals 3, which is this horizontal line-ish, and then y equals whatever the heck that is. So what is that, this line here? They give you 2 points, so you should be able to kind of figure it out. So the points are going to be 0, 9er, and then 3, 0. So the slope, y2 minus y1 is negative 9, all over x2 minus x1 is 3, so that would be negative 3. So y equals negative 3x plus the x-intercept, which is 9, so that would be your upper bound. Y equals negative 3x plus 9. And then the outer limits, it looks like we're going from 0 to 2, maybe. You need to be careful, though, and kind of look at where they actually intercept. So set the two curves equal to each other. 3 equals negative 3x plus 9. So negative 3x, 9, negative 12. So x is serial. No. Y is 3, and I'm trying to figure out where this stupid curve hits it. And there's no way it's 4. So maybe this curve I have is wrong. If I put in 3, that works. So what the heck's wrong with this? Where do they intersect, man? They have to intersect at like 2, you know? Oh, I see. This is negative 6. There we go. So x is 2. Sorry. Right. So it looks like I'm going then from x equals 0 to x equals 2. So 0 to 2. Okay. I feel better about the universe. So 0 to 2, and then negative 3x plus 9. Let's see if it lets me figure out if that's right before I go and integrate, right? Yeah, okay. And then I'll go ahead and integrate it. So I have the integral of y from 3 to negative 3x plus 9 dx. So I have the integral of negative 3x plus 9 minus 3 dx. And that'll be the integral of negative 3x plus 6 dx. And then that will be negative 3x squared over 2 plus 6x from 0 to 2. And then that will be negative 3 times 4 over 2. That would be negative 3 times 2, which is negative 6, plus 12 minus 0, which will be 6. Okay, so those, it's curve to curve and then point to point. And they're relatively easy, except when you kind of have multiple regions to deal with. And I'm looking for an example of that. And down here, oftentimes, well, not often, but sometimes you're going to need to have 2 different integrals to deal with the multiple region issue. Let's see if I want to deal with one of those right now. Yeah, so they are quite annoying, so let's just get one of those out of the way. So number 26, I have the integral from 0 to 2, and the integral from 0 to x, dy dx, and then plus the integral from 2 to 4, the integral from 0 to 4 minus x, dy dx. Okay, so the first thing that's different about this problem is we kind of need to draw the area based off of the integrals. Okay, so that first integral, you're thinking again, it's always this idea you're going from curve to curve, and then with this orientation it's y equals to y equals, and then x equals to x equals. So in the inner integral, y equals 0 is this line. And I want to be sure that I only go from 0 to 2, so I'm going to make that explicit. I want to go from 0 to 2 right here, my point-to-point part. But the curve part, y equals 0, is this curve to y equals x, which is this curve. Okay, so I have this region first off from the first integral. Then the second integral, I'm going from y equals 0 to y equals 4 minus x. So the curve 4 minus x has an intercept at 4. So what is this point? If it's y equals x, that point has to be 2, 2, right? Because the curve is y equals x. So 4, so this is 1, 2. The y equals 4 minus x right here that I'm talking about. So on my second integral now, I'm going from y equals 0 to y equals 4 minus x over the interval from x equals 2 to x equals 4. So the second one is going from 2 to 4 here in that range. the first curve, y equals 0, again is just the x-axis, but the second curve is this y equals 4 minus x, which is what I'm trying to draw. Okay, so the intercept is at 4, and then it's going down 1 over 1. So it'd be right here, and then down 1 over 1, it'd be right here, down 1 over 1, be right here, down 1 over 1 is right here. So I can kind of piece that together and get this curve. And so y equals 4 minus x, I'm going from, again, y equals 0, this curve, to y equals 4 minus x, which is this curve, and then to the 4. So the second integral is this region here. Okay. So if you see over here, they give you 4 regions to pick from. It's that first curve. One thing they'll want you to do is change the order of integration. And in this case, changing the order of integration will make your integral much easier. And that happens sometimes. So to change the order of integration, now we put dx dy. And we'll be going from some curve x equals to some curve x equals, and then points y equal, and it's looking like we're going to go from y equals 0 to y equals 2. Okay, so in the first orientation, you kind of think like you have a person like this, right, going in this direction. And the other orientation, you kind of think, oh, I have a person going like this, going, what I always say, up the flagpole. Okay, so in this second orientation, the bottom curve, let me put the bottom curve in blue, would be this curve. And then the upper curve, let's put that in green, is then this curve. Okay, so x equals this blue curve, which the way we've written it right now is y equals x. So x equals y. The bottom curve is y. And then we go to the green curve, which I'm going to have to solve for that, right? So originally it was 4 minus x. Add the x to the other side, subtract the y to the other side, so you get 4 minus y. So x equals y to x equals 4 minus y. And in this orientation, much simpler, curve the curve, and then point to point. It looks like we're just going from 0 to 2. And, we just have one integral to deal with, so life is much easier. So let's go 0 to 2, and then x, they even help you out, x is y to x is 4 minus y. And then they want you to evaluate it. So it's going to be the integral of x from y to 4 minus y dy. That'll be the integral of 4 minus y dy. So that'll be the integral of 4 minus 2y dy. That'll be the integral of, oops, let's just integrate, shall we? So that's going to be 4y minus 2y squared over 2, so y squared. Evaluated on the outer bounds now, 0 to 2, so that's going to be 8 minus 4 minus 0, so that's just going to give you a 4. Okay, let's make sure it's all right. Okay, so that's one of the nastier ones. Let's go back a little bit and deal with maybe an easier one. So in number 22, again, this is one where you have to first sketch the region and then integrate it. Let's do this one, and then we'll jump back up to 21 for the other orientation. So this one, 22, we have the integral from 1 to 4, and then the integral from 0 to ln y of f of x comma y dx dy. Okay. Well, this is the unusual orientation. So start x equals some curve to x equals some other curve, right? Okay, so in this orientation, like I said, your little guy is going up the flagpole like this, and I'm going from x equals 0. So x equals 0 is the y-axis, this curve here, to x equals ln y. What the heck is x equals ln y? What is that? Well, you can exponentiate both sides. You get e to the x equals e to the ln y. And so e to the x equals y. It's just the exponential function. Okay, so it's just this curve right here. So in this orientation, curve the curve, y equals, or sorry, x equals 0 to x equals ln y will be this, and then point to point. So where is that? Is 1 at that intersection point? Maybe that's a good question. So x equals ln of 1. Just trying to figure out where the heck the y-intercept is. So x is 0 at the y-intercept, and then you have to solve this equation, right? So exponentiate both sides, or you could just say e to what power, e to the 0 power is equal to y, right? Because ln is just log base e. So you're saying e to the 0 equals y, so y must equal 1. So yeah, that point right there when the intersect is 1. So you're going from point 1 to the point 4, and it must be this region right here that you're worried about. Okay. All right, so let's see if we can find that. Yeah, it's this one here. And then they want you to, apparently, I don't know what the heck that is. What the heck is that? Oh, they want you to change the order of integration. Okay, so if you were integrating like in this other orientation, like this, curve the curve in that case. So we've already kind of solved for this function. It will be y equals e to the x to y equals 4 on the integral. Y equals e to the x to y equals 4. And on the outer integral, we're going to be going from x equals 0, apparently, right here to whatever this point is here. And we know the y coordinate there is 4. We just have to figure out the x coordinate. Okay, so you can go to your formula, wherever the heck it is. So x must equal the ln of 4 right here. So I'm going from 0 to the ln of 4, and then our integrand is just, it is whatever it is. They're not telling you what it is. So 0 to ln 4, and then y equals e to the x. So curve the curve, point the point. So put that on my, those are my dying words. Put it on my gravestone, you know. That idea should get you through the majority of these problems. Let's do one more. Okay, let's find one that's relatively interesting, maybe. None of them are really all that interesting. Okay, so I'll do one more and then we'll leave it there. This one looks kind of weird because it has this weird upper limit. I think we pretty much hit the big and the small in the book, comparing different orders of integration. Two integrals, that's the one here with the two triangles. You have to split it up into two regions. So that first region would be going from this line curve to the parabola, and then there's another region from y equals, or x equals 0 to y equals the parabola. But we kind of already did that. Okay, yeah, I think we hit it all. So let's hit this one last exercise. We'll make this one the video quiz as well. So this is video quiz set number 7. This will be the first problem in that set. This is problem 27. Okay, so 27, we're in WebAssign, and this is the video quiz. Yay! So I have the integral. First I got to sketch the region. X equals -2 to the 2, y is going from 0 to 4, or x is going from 0 to 4 minus x squared because it's dx dy. Okay, so the curve x equals 0 is just the y-axis, and then x equals 4 minus y squared is kind of a sideways type parabola, right? So again, x equals 0 is the y-axis. If you want, you can already say that the sort of the y values the guy is going over. It's going from -2 to 2. But anyways, x equals 0 is the y-axis to x equals 4 minus y squared. 4 minus y squared, that curve is a parabola flipped sideways and then shifted up 4 places. So 1, 2, 3, 4. And of course its intersects will be at -2 and 2, so it's going to go through there like this and like this. So curve the curve like that, and then point to point. That would be our picture. Okay, so that's this picture. And then they want you to change the order of integration. Okay, a technique we need to do because sometimes integrals won't be doable in the original order that you kind of have made. So in this other orientation, if you want to go curve the curve, okay, well, first off, point to point on the outer part of the limits, you're going from 0 to 4. That's pretty obvious. So point to point, right? But the curves y equals to y equals, that's going to be from that parabola. Originally, the parabola again is given by x equals 4 minus y squared. So I want to solve for y, okay, in order to go from curve to curve. Right, and there's going to be 2 different curves. There's this curve here, this one branch in blue, and this other branch I'm putting in green. Okay, so I get y squared equals 4 minus x, and then y equals plus or minus square root of 4 minus x, right? The plus version is the green curve, the minus version is the blue curve. So going from curve to curve, I'm going from y equals negative square root 4 minus x to square root 4 minus x, positive square root 4 minus x. Okay, so let's see if that's right. 0, 4, and then yeah, looks like it's going to be right. Square root 4 minus x. And you could always, I think you could check it and it's not going to count against you, like if you didn't put in one of the answers. See, it doesn't really mark it wrong. That way you could check to see you got it set up correctly and go from there, right? So dy dx. Okay, so the inner integral is going to be y evaluated from negative square root 4 minus x to square root 4 minus x dx. Substitute in the limits, so you're going to end up with square root 4 minus x minus negative square root 4 minus x, which will be plus square root 4 minus x dx. So I give you 2 of those. You can factor out the 2, and then you have square root 4 minus x dx. You could do a u sub on that. It's going to give you a negative floating about. So you have -2 integral u to the 1/2 du. And then power rule that character. So you get u to the 1/2 plus 2/2 is 3/2 times 2/3. I'm going to remind myself to evaluate. -4/3 back subbing, that's a 4 minus x to the 3/2, and we're evaluating from 0 to 4. Okay, plugging in 4, of course you just get 0, and then minus -4/3, plugging in 0, you get 4 to the 3/2, which is 8. Okay, so that first part is 0, and then you get 32/3. Okie dokie. 32/3. Make sure it's right. Hopefully it's right. And yay, all is well in the universe. So as usual, thank you for watching, and we'll see you next time.